Okay, in this video, we want to look at a direct proof involving divisibility. And so in order to start out, let me make a definition, which is to say that a non-zero integer, a, is said to divide an integer b if b equals a times k for some integer k. Okay, nice. So then when a divides b, we write a with a long vertical line, and when a does not divide b, we write a does not divide b. Okay, good. So this is a definition of what it means for one integer to divide another. And this is important because throughout the class, we'll do examples of proofs, and from time to time, I'm going to want to do proofs involving one integer dividing another. So it just gives us something else that's fairly simple to try to prove things about. And also it's the kind of thing that you would study in like a number theory course. So if you take number theory, you will study this kind of thing and prove lots more about it potentially. And so let's just start with some simple examples to make sure this makes sense. So of course, 2 divides 24, since, well, we can write 24 as 2 times 12. So k is 12 in this case. 3 divides 66, since 66 can be written as 3 times 20, 3 times 22. 5 does not divide 37, since 37 does not equal 5 times k for any k. Notice that when you want to say, just looking at the statement itself, we want to say that something does not divide something else and then provide justification. You cannot just give an example. Now you have to make an argument of sorts. At least when I expressed it, I had to say that this wasn't the case for any k. Right? We just want to take note of that because that's going to be a common thing throughout proofwriting in general. Sometimes to prove something, you just give an example, or to disprove it, you give an example, and other times you need a a general argument, right? And then lastly, 7 does divide 28 because 28 equals 7 times 4. Okay, enough examples. So what do we want to prove about divisibility? So here's the proposition that we want to prove. Let A, B, and C be integers, and if A divides B and B divides C, then A divides C. Okay, so this is a nice little proposition that we can prove now to practice a direct proof involving divisibility. And this kind of property, you have to kind of squint your eyes and try to abstract away what I'm about to say. I'm not talking about divisibility specifically, but a property like this is called transitivity. So you'll see something called transitivity throughout mathematics in various different places. And it usually comes in this kind of form, like A is related to B, B is related to C, and hence A is related to C. Here, of course, when I say related to, I should be more specific. I'm talking about divides, one thing divides another. But the transitivity part is the fact that there is this relationship between A dividing B, B dividing C, and that implying that A divides C. Anyway, you don't need to understand transitivity so much yet. I'm just making that comment since it is true, and you'll see this in other places. For now, we can just play around and prove this, right? So first, again, we should just kind of play, right? Let's do some scratch work and play. We might be able to just go right into this proof, but let's develop a reason why we think it's true first. So let's take an example. So 3 divides 12 and 12 divides 48, right? So then does 3 divide 48, right? Okay, so well, we can just check, I guess, right? So 48 is equal to 3 times 16. So the answer is, so yes. Now that alone is not very helpful. So the question is why, right? Okay, so first of all, 12 is equal to 3 times 4, and 48 is equal to 12 times 4. And so the point is that I can use my previous observation about 12 being 3 times 4 to say that, sorry, to say that 12 is equal to 3 times 4 times 4. So this whole thing is like 3 times 4 times 4, and that's like 3 times 16, right? So the point is that because 12 divides 48 and 3 divides 12, I can rewrite the 12 that occurs in 48 using 3, right? So in general, that's going to be the case, right? So we'll just notice that if A divides B, then B equals A times K for some integer K, but I'm just doing scratch work, so I'll not worry about being too careful yet. If B divides C, then C equals B times L. Let's even not even worry about the for some part because we're just playing right now in scratch work. And so if we look at C, C is equal to B times L. And just like we did with the 12 before, I can rewrite the B as A times K. And then if I like just to really make it pretty at the end here, we can make it very clear that that means it's A times some integer, right? Okay, but now we should write up the proof carefully. It's not going to be a very long proof, but again, a big part of this course is actually writing things carefully at the end. And I notice with students sometimes they can even understand the insight or the idea of the proof, and that's very important. But then they struggle with writing it down in a way that someone else can understand. And that's equally important, right? As human beings, we have to be able to communicate ideas to other people. So it's great that you understand, but um, you know, you have to also work at being able to communicate to somebody else. And also, when things are complicated, sometimes you can convince yourself that you understand the proof. And then when you're forced to write it down, you realize that you do not. So any good mathematician has had this experience, including myself. So, okay, so let's assume that A, B, and C are integers so that A divides B and B divides C. So we're just introducing the setting to the reader, and now we're going to unpack what A divides B and B divides C means by definition. So then, by definition 2.8, we just kind of use this. B is equal to A times K for some integer K, and C is equal to B times L for some integer L. Good. And then hence, now we're going to do the main calculation, which proves the proof. B times L is equal to, well, it's equal to A times K times L. And let's just isolate the A. And then just to bring it home, since K times L is itself an integer, we know that A divides C by definition 2.8 as desired. Okay, so that's the end of the proof. Not a very long proof, but it just points to one more example of something we can prove directly oftentimes, which is statements about divisibility. And I'll have you do an example in one of the worksheets.